quantum computing with the probabilistic nature of output turns out to be a great fit for some of the machine learning and deep learning applications. So our research is not pretty much on hardware development. There are definitely a lot of physics and material scientists that try to develop hardware. My research group pretty much focus on the software end, or in particular focus on algorithms and use cases or applications. And the main idea is that now we are given this hardware, no matter it's by IBM, by Google, by IonQ, or any kind of vendors. There could be a variety of problems that we have to deal with in the broader area, artificial intelligence, data science. So the question here is, how can we develop effective quantum algorithms along with certain programming details, architectures, pretty much everything from the computational computer science perspective in terms of software, using the available quantum hardware to address some of the important problems that we could see right now in this space, in the AI space in general. All right. And some of you may argue that, it's too early to do that because, the hardwares are still not so mature. The machines are still in the early stage. Maybe we have to wait for 10 years or even longer to revisit this problem. Here, I do want to bring in an interesting story that many of you probably have heard about. This photo is, Alan Turing, as you may know. We had a Turing Award presenting yesterday, right? So Alan Turing was pretty well known in history, of course, because of many contributions he made in the computer science, but also because he built this machine called BOMB, B-O-M-B, BOMB machine. This was a U.S. Navy bomb machine back in 1940s, right? So this bomb machine was able to break the military code used by Germany and its allies and help to save thousands of millions of lives. So see, if you compare this bomb machine with the computers we're using right now, they're completely different. This is very much a specialized machine, very bulky, right, compared to the lady here, and probably not performing that well. But even with this kind of special purpose computer, special purpose device, which is in early stage of the computing history, there were some very, very impactful applications that we could explore and use them to help the society if we know how to develop right algorithms and right AI tools. So that's the main argument I want to make here today. So right now we are pretty much in this called NISQ stage. This small figure was motivated by the earlier one by Professor John Prescott, and of course coming up from our recent review paper. So what we call NISQ space is that we're in it's called noisy intermediate scale quantum. Okay. So in terms of number of qubits, what you can see is that the major players like IBM, Google, and Honeywell are still in the range of from 10 to 100 qubits range. In terms of error rates, they are pretty much in the 10 to the minus 2 to the minus 3 range as well. So eventually, we are hoping to get into this fault-tolerant quantum computing, and it will require us to get to like millions of qubits. But it's going to be a long way. Google predicted they need about 7 or 8 years from now to reach that. But for now, at least with the current machine, we could only look into some of the near-term applications. So the major use areas in the NISQ space, at least in the next few years, next few decades, even before this hardware become large-scale commercialized, will be in 3 domains that we could talk about. And the first one is computational chemistry. Right, chemists use quantum computer quite a bit. They've been running its quantum chemistry calculations. And this one is less relevant to AI and data science to some extent. But the other two are directly connected to AI. Right, the second one is on optimization, and the third one is on machine learning that includes deep learning. So let me just use one slide, very briefly talk about this computational chemistry. Apparently, this is not my area. I know a little bit chemistry, but I don't think I'm qualified to be considered as a computational chemist. Fundamentally, we know about this chemistry or simulations, either quantum mechanics. There's a boundary in theory, right? But with the quantum computer, there's the potential speed up that you can bring in to break this classical boundary. And eventually, you can use it to compute this called full configuration interaction solution to the electronic Schrodinger equation. And to some extent, you can see these quantum computers are pretty much, consistent with the quantum mechanics calculation. And the major application is to bypass the classic boundary and expand the, solution space to a solution of large, much more complicated molecular and, chemistry problems. And again, this is not my area of research to some extent, but I do want to acknowledge that as one of the very active area of research nowadays. So in the AI space, our approach, at least in my group, our effort is try to use this interesting illustration here. We call hybrid classic quantum computing. All right, it's not going to be 100% quantum because quantum machines are not mature yet. But we are not going to, rely on classic too much either. So that's what we said is big elephant on the quantum, elephant, the classical elephant in this big quantum room. And that's the nice illustration from Zapata that they put these elephants with all digital binary classic computing systems, 0, 1, and then carrying a, quantum processing units and tower layer. So one of the popular approach that you may heard about is called variational approach, VQE, variational quantum eigensolver, for instance, that many of you know. Sometimes solve for quantum problems and then solve a classic problem iteratively until you get a solution. This is a very popular approach as one of the special case of the hybrid classic quantum computing. So we have been exploring this into a few domains, as you can see from this overview figure. And let me focus on the right-hand side here. In particular, we look into quantum deep learning, which I'll talk about it briefly later on. And then we also look into quantum optimization that I could focus on in the next 2 or 3 minutes. So for quantum computing for optimization, pretty much we have a wide range of optimization problems that we have to solve, right? From mixed integer linear program, nonlinear program, mixed nonlinear program, and so on. And at this moment, at this time, there are provable algorithms that you could use some sort of quantum algorithm to solve problems like linear program and semi-definite programs. In theory, they could reach out certain speed up in theory, but in practice, we do need a large number of qubits to solve large problems. The other class of problem that we could demonstrate much advantage using quantum computer would be something that we could formulate as a QUBO, quadratic unconstrained binary optimization problem. So this will spin over from integer linear program to constrained integer nonlinear program to even integer nonlinear program to some extent. But it's a pure discrete variable based approach. So it's a very special class of optimization problem that if you could formulate it and embed it into some sort of quantum hardware, then this quantum system will solve it very effectively. So the fundamental philosophy, as illustrated in this figure here from our recent paper, is that eventually, in the long run, if we have this fault-tolerant quantum computing, we can use quantum SDP, semi-definite programming solvers, or quantum QA/OA, quantum approximate optimization algorithms to solve fairly large problems, right? And this is called BQP. Some of you may know that from a computational theory perspective, it's called bounded error quantum polynomial time problem, and this involves P, which is polynomial time algorithm. And we have this NP complete, this black box, and NP high in this bottom part here. In the NISQ space, which is the near term we are facing right now, we may either use quantum annealing, which could deal with QUBO, or we may use some sort of NISQ algorithm for SDP in this space. So there are quite a few applications that actually you can use quantum computing for optimization right now. That recently BMW has a challenge, for quantum computing for their sensor placement problem, and it was quite successful. So let me give you a quick illustration about some of the efforts we did in this space on quantum computing for optimization. This is really focused on a specific type of problem, which is quite well known to some extent, called job shop scheduling problem, right? We have to schedule the jobs. This has many applications from manufacturing to aerospace to any kind of routing problems to some extent. The objective is fairly simple. We try to minimize the processing cost defined by time and by cost, monetary values and so on. And there could be constraints, the assignment constraints, due date constraints, release date constraints, sequencing constraints, and so on. The results could be produced and presented by Gantt charts. So one typical approach that you could use to solve this problem is to formulate it as a MIP, mixed integer linear program problem, with integer variables to represent the sequencing assignment decisions. And we have a whole bunch of constraints dealing with timing, with assignment, for the sequencing, and for logic cards, and so on. So the challenge is that this is a mixed integer optimization problem. So if it's large scale, then it could be very hard to solve, and it could take a long time. So what we did is we come up with a hybrid algorithm, quantum and classic decomposition-based approach. The idea is that, of course, if some of the jobs cannot be scheduled on a particular machine, then it will be impossible to find feasible schedule. So this is more kind of problem-dependent relaxation. In the same concept as we did, relaxation in solving integer point problems. So you have a relaxed MILP, we drop the sequencing constraint, and then we can easily formulate a problem in a form of QBO, quadratic unconstrained boundary optimization. They could fit into a quantum computer and solve quickly using a QC step. So I would like to say that this whole method was motivated by some earlier work by Ignacio Grossman, published in Info of General Computing. But in that case, he was using the constraint programming in this setting. So the key idea here is that we solve a relaxed mixed linear problem in a classic machine using solvers like CPLX, Gurobi, and so on to solving them, effectively and efficiently. And if the problem is feasible, we will be able to come up with some sort of a primary solution or partial solution, and then formulate another problem that we could solve on the quantum machine. And this quantum machine by all means could solve very, very quickly, in usually microseconds or milliseconds. And we get a solution which is feasible or suboptimal. Then the very unique piece here of our framework is that we add integer cuts iteratively throughout this process. And this is very crucial because one major argument or major criticism of the current quantum system is that the solution is probabilistic. There's no guarantee of global optimality. But by using this kind of iterative framework, some sort of variation approach, but more importantly, I would rather call it hybrid decomposition-based approach, we could guarantee the global optimality in theory. Okay, and this is something that has never been done before by any existing quantum algorithm, because almost all the quantum computing methods for optimization are pretty much heuristic in a certain way. And this is the first time that you will be able to combine it with classical methods and obtain this global optimal solution. So let me quickly show you some results. This is a study we worked together with Oak Ridge National Lab, right? So as the problem size grows, when we have more jobs and more machines to solve, we use the best classic solver, Gurobi. If you're in the optimization or mixed linear programming space, you probably know Gurobi, which is, the best classic solvers, highly optimized and very tailored for many applications. And you can see that when the number of jobs increase to 80, pretty much the Gurobi cannot return any solution, either running out of memory or reached any kind of resource limit. While the hybrid ones was still able to get a solution within certain reasonable times. And in many cases, the solutions are pretty good or comparable to the ones you can obtain from the classic computing systems. There are many other case studies with all applications also explored. Due to the time limitation, I will not get into details, but fundamentally, this could be used to solve problems ranging from very small scale molecular design or drug design to manufacturing systems to even logistics and supply chain optimization across different scales. With the next, let's say 5-10 minutes, let me quickly jump to the second part of the talk, which pretty much focuses on quantum machine learning. I think many of you probably are more interested in this area because it's really a combination directly applied to the AI space. And I would argue that quantum machine learning, it's relatively new, okay, but it's growing very, very fast. There are quite a few, software packages right now that you can really leverage, ranging from, PyTorch TensorFlow that have quantum versions to some other systems like, Strawberry Field, PennyLens, and so on. And IBM has Qiskit, they could run these, and Rigetti also have Rigetti Forest. But fundamentally, all these quantum machine algorithms could be classified into a few groups. In the near term, we pretty much focus on something that is simple enough, like, based on annealing, the orange circle, right? Annealing is a direct application area. They connect quite closely with optimization. And then in the next few years, we probably will see more and more application of global search, okay? Global search was proposed by Dr. Lev Grover, actually when he was a faculty member at Cornell University as well. Later on, he did not get tenure and moved to AT&T Bell Lab. Okay, but Lev Grover. But when he published the paper, it was not popular at the moment. But now everybody knows global search. And then quantum neural network was even longer term because we do need large number of qubits to form the network architecture. And even longer term will be phase estimation and so on. So one of our major invention in this space is a hybrid quantum computing approach with the specific application to fault detection and diagnosis. All right. And this is a very special kind of application, which is very important because in any kind of fault detection diagnosis applications, we want to get answer quickly. We want to get a decision or prediction very fast. The sooner the better. So here we leverage quantum generative training in this space to develop this conditional research Boltzmann machine, which is one kind of deep neural network, deep learning model, initially proposed by Professor Geoff Hinton. One very unique piece here is that we train each layer, not only because the architecture is unique, also the way we train it, it's very unique because we could train each layer sequentially. And here we leverage two major pieces from quantum computer to help with the task. First one is quantum sampling. Pretty much, the training process involves quite a bit of sampling. So, quantum computer will help us to run sampling quickly. And the second one is use quantum machine for optimization or for training. Because when you say you train a neural network, it's pretty much optimization process. And for RBM, for research Boltzmann machine, this tends to be a perfect case for optimization for training, quantum optimization for training. Then after that, we will have the fine-tune stage, looking at discriminative training, and this will be performed in the classic computer using all these, classic architecture as you see, from full reckoning layer to ReLU, full reckoning layer, softmax, and so they eventually run some classification outcome. So one application which was done a couple of years ago during COVID, we are still in COVID by the way, a couple of years ago, focused on cyber physical systems. And this is a very classical problem, Tennyson-Eastman chemical process, which has 15 dimensions, 11 manipulated variables, and 41 major variables, and there are 2140 data sets. Okay, so we try to detect the faults of TE problems. A quick comparison is this kind of training cross entropy loss. The red one is by contrast divergence algorithm. For those of you that are familiar with contrast divergence algorithm, there was one also proposed Geoff Hinton when he invented research Boltzmann machine. The green one is the quantum-based approach. And apparently, by looking at cross entropy loss, you can see the quantum one converges much faster than the classic ones in terms of the outputs. While the outputs are pretty much similar, we will say there are clear quantum advantages. I would not say quantum supremacy, but there are certain quantum advantages as the process complexity increases. You could easily scale up to large problems. But this application is not as significant to some extent. All chemical process need to be, safe for sure, but the results is somehow comparable. Another application which is more interesting, it's an electric power system space. This is a very standard IEEE 13 bus system. For those of you that are involved in smart grid or power system engineering, you probably see this quite often. And this data set has 90 dimensions, 3-phase voltage data recorded in each bus, then 40 data sets, and many faults introduced after 500 and 200 or more samples. So there are symmetric faults and asymmetric faults, right? Here we're looking at two different indicators. Both of them are very important. First one is called MDR, and second one is called FAR. MDR means, means detection rate. For means detection rate, of course, the lower the better, right? The second one is called false alarm rate. False alarm rate is also the lower the better. You don't want the alarm to be, trigger all the time when there's not supposed to be doing. So what you can see is that our approach tend to yield very, very nice results, almost close to zero in both cases. But now if you compare with the classic methods, the misdetection rate is pretty much horrible. And some other applications that, some other implementations that they are using in literature, using decision trees, using discrete variable transformation with neural networks, none of them could get to the level that we have, right? So pretty much the classic methods produce minimum false alarm rate, but maximum, misdetection rate. And other methods that is in tree and artificial neural nets tends to be not performing that well. And the other thing which is also quite important is the computational efficiency. Basically, you can see the red one is the classic ones and blue one is the quantum one. Then in this case, you look at the free energy, there's a clear convergence, efficient convergence in terms of apples. And looking at sampling time and scaling, right? The orange one and the blue ones are more for classical approaches for different versions, while the green ones is the quantum version. And you can see scales with the dimension almost flat, right? So you can scale very quickly. So this was a story came out last year, a few months ago. I mean, there's a new story. There's a tying up quantum computing to AI could promote a smarter power grid. It was also featuring communications of ACM and also HPC wire. If you're in the high performance computing domain, you probably know HPC wire is a major medium. So that's pretty much the end of my presentation. So I think right now, hopefully through this short presentation, I give you a flavor about what quantum computing it is, right? It's pretty much a very exciting time, but I would say still very much in the infancy, although there are many exciting developments going on right now. And in certain way, you could see this is more like a very first flight by the Wright brother, in 1903 or more than 100 years ago. The very first flight, has a top speed of 30 miles per hour. And the maximum distance they get was only 815 feet. That's not too far away, right? In the same time, or even earlier than that, 1902, the trains could travel at 65 miles per hour and could run thousands of miles across continental US. And same for the cars, right? But by all means, these are just two different groups of technologies. Airplanes now could fly much faster, much longer than 100 years ago, and that's because these are different technologies, even though we are in the early stage right now. So the future is bright, but eventually to implement these technologies, we do need a combination of both in many ways. Quantum computing will not be the solution to all the problems, but it could be helpful to some application in science and engineering, ranging from molecular materials to manufacturing process and to energy systems. So last but not least, there's a recent perspective article that we worked together with folks from NASA and ExxonMobil, trying to cover some of these perspective of quantum computing. You are very interested, take a look if, this is something of interest to you. So let me finally acknowledge my research group. That was a photo we took last year. We're going to have a new one in a few months and some beautiful photos of Cornell campus. Thank you very much again. I don't know if there's any time for any Q&A, but I'd be happy to answer any question if there is any.
Okay, thank you very much, Professor Yeo. Thank you very much for this very enlightening talk. I guess due to time limits, we just allow one question. I got a quick one. Based on your presentation, we have observed clear advantages of quantum computing for achieving much higher efficiency and better performance compared with our nowadays regular computers. Yeah. So do you have any projection how fast these quantum machines can be commercialized to everyone? And so we are very expecting that.
Yeah. Well, that's a very good question. I think the machines are already being commercialized now. I think everyone could really access the IBM quantum machine, for instance, for free actually. So they're already available. I think the challenge right now is that they don't have that many number of qubits. They don't have enough quantum bits. So the size is still quite small. But they do have very ambitious nowadays IBM, Google, or other vendors. I cannot speak for China because apparently Chinese government also spend a lot of resource in building these machines. But I think many people predicted by the end of this decade, by 2030, we should have thousands of qubits or millions of qubits. They could even break down some of the cybersecurity issues in certain way. And by that time, I think many problems could be always solved at large scale already. Yeah.
Okay, thank you very much. Thank you for Professor Yeo's very nice talk. And hope after pandemic we can have more interactions and we can have you visit on campus at City University of Hong Kong. Yeah.